So we now begin several sections on the weighty applications of derivatives, and it begins with a bang here with related rates. Related rates, um, a challenging section for a lot of students when I teach it, so get ready. Um, but definitely a really once you get your head wrapped around the steps and how to think through these problems, very powerful things we can get from this. Okay, so let's just first kind of do something that's not applied yet. We'll get to the examples. We're going to look at this right here. Um, okay, implicit differentiation of x and y with respect to t. So this is going to like set the stage. We're going to do an example. We're going to look at x squared plus y squared equals 25. So if you remember implicit differentiation, we had things like this, right? An implicit equation, and we took the derivative of both sides with respect to the independent variable x. So we wrote d over dx, bracket d over dx, bracket to each side. And I'm sure you guys remember this. And whenever you took the derivative of y, you did it normally, but then, at the end you wrote dy over dx to represent like the chain rule happening on y, the derivative on y. Okay, so we're going to remind ourselves of how that procedure works, but then we're going to add this extra twist. So related rates, you're always going to have these two quantities. Just call them x and y, but they're going to be with respect to this third variable t. So what's happening is, I'll just show you this part. The independent variable is t, and there are two dependent variables, x and y. So we can think of like x is a function of t and y is a function of t, and then x and y are connected in some equation. Okay, so what does this look like just to get our bearings? Let's do the implicit differentiation of x and y with respect to t for this guy right there. So what we'll do is we'll write d over dt applied to both sides. Since it's with respect to t, d over dt for the left, d over dt for the right. Okay, and then now how does that work? Okay, well, t is a different variable than either x and y. So when we take the derivative of x squared, we say, all right, we'll do it normally, and then we'll multiply by dx over dt. And similarly for y squared, take the derivative normally, 2y, but then the chain rule, then we'll multiply by dy over dt. So now that, that dx over dt, dy over dt, it's happening to both the x and the y since there's now this third variable involved. Okay, so it's like taking implicit differentiation one step further. Although the derivative of a constant is always still 0, so we still get the 0 over there. And I think this gives us enough practice just to get our feet under us of where we're going to go in examples. This also explains the name of the section, related rates. As you notice here in this equation, we've got a dx over dt, of course, and a dy over dt. Well, those are both derivatives, and we know derivatives represent an instantaneous rate of change. And so that's the rate of x with respect to t, and that's the rate of y with respect to t. And these two rates are connected in a bigger equation, so we know how they are related to one another. So they're related rates, literally. Okay, now that we've set the stage, let's get into our first example. These examples, they're a few sentences long, so I apologize. You'll have to take a moment and write all this down, or maybe you just do the example. I don't know what your note-taking style is. I'll go ahead, excuse me, I'll go ahead and read it. A 72-inch ladder is leaning against a house where the base of the ladder is 36 inches away, meaning 36 inches away from the wall or the house at the bottom. The base slides away from the house at 5 inches per second. So you imagine the ladder's leaning against the house, but then the base slips and it starts to push away from the house, and the whole thing starts to collapse. And they tell us how fast that base is sliding away, 5 inches per second. Okay. So the question is, how fast is the top of the ladder sliding down the house, right? As the base slides away, the top of the ladder like scrapes against the house as it falls. And so how fast is the top sliding down? And that's definitely going to be different than the base because it's at an angle. And okay, we'll round to 2 decimal places and we'll include the units. This is a classic related rates situation. So it's a perfect one to get us started. So here's what we're going to do. This is all we have to go on, right? They don't give us an equation. They don't even tell us what the variables are, right? It's just this description of a scenario. Okay, so it's critical that we begin a question like this with a drawing, and then we go in and we label the drawing of what they tell us, in the question, but then we label some variables into that drawing as well. Okay, so here's what we've got. And we're going to add more to this drawing as we read through it again. But okay, so we've got, the house. The house is like over here, right? And down here's the ground, right? It's like the grass or who knows, cement or something. And then we've got the ladder, right, leaning at an angle. And they tell us the ladder is 72 inches long. So I'm just going to label that as 72. It's like a 6-foot ladder. Okay, so then let's kind of read through it. The 72-inch ladder, the base is 36 inches away. Okay, 36. Now at this point, it's very tempting to label this distance as well, but don't do it. Here's why. This distance is changing, right? Because the base of the ladder right here starts to slide this way. So we don't have a fixed length there. So we don't want to label it with a number. The ladder is a fixed length. It's always 72 inches. But this distance changes. This is going to push away. And it says the base slides away at 5 inches per second. So I'm just going to put a little 5 there. It's pushing away at 5 inches per second. So then it says, how fast is the top of the ladder sliding down? So we know this is coming down this direction. And we can just visualize this thing as it collapses. Okay, so far, we've got a good start, but we don't have any variables yet. We really need to incorporate some variables. Here's what we're going to do. The variables represent quantities that are changing. Okay, let's kind of write that out. Variables represent quantities that are changing, or you might say in motion. So what two quantities are changing? This length here is changing, right, from the base of the house to the base of the ladder. And I'm going to call that X. It's a horizontal distance there. Also, right, the distance vertically right there, that's changing as the ladder comes down. Let's call that Y. Makes sense because it's vertical. Okay, now we're in a good position. We got our picture, we got some variables in there. We also notice that we've got a triangle, right? And in fact, that's a right triangle. So maybe we label that as well. And okay, so far so good. What do we do from here? Once we have a drawing, we want to, from that drawing, we want to get an equation that relates our variables. So here we've got two variables, x and y. And if you just look at that picture, is there, and this is challenging. One of the reasons why related rates is challenging is now no one's going to tell you, you just think of all of the math you've ever learned. Is there some way, an equation, that you can connect x and y? Okay, so maybe this one is, whenever I teach this course, I kind of at this point ask, what's an equation we can use? And a good number of students know the Pythagorean Theorem, right? So we've got a right triangle, we've got the lengths of all three sides. And so we would know, a squared plus b squared equals c squared. And yep, that would do it. So in this case, that would look like x squared plus y squared equals 72 squared. And I'll go ahead and slide this up at this point. Okay, so from our drawing, we get that equation. Oftentimes, just getting this equation is the hardest step in the entire process. Just to get to an equation, right? When we did implicit differentiation, right, they always told us the equation. Like, here's the implicit equation. Now take the derivative and solve for dy over dx or whatever it was. Here, they're not going to do that. They're going to tell us variables. We got to set all this up. We got to create the variables, and then we got to see the equation that connects those variables. Once we have the equation, then it's going to feel a lot more like those implicit differentiation questions. From here, now we can take the derivative of both sides with respect to t. Okay, and so we say, all right, well, it's really much like that first example we did, right? X squared plus y squared equals some number. So when we take the derivative with respect to t, we get 2x dx over dt plus 2y dy over dt. And you notice we don't even need to square the 72. We could figure out what that number is, but we're going to take the derivative. It's 0, whatever that number is. It doesn't matter. Okay, we've made a lot of progress. We now have our related rates equation. Dx over dt, this is how fast x is changing. And they actually told us that, how fast that's changing at the beginning. Dy over dt, that's how fast the y value is changing. Okay. At this point, what we want to do, I'm actually going to slide this back down. We need to go back and read the question again and identify which of the two rates they're asking about. And maybe that's not really necessary here. We get it. We got a nice drawing, but I'm going to do it again. How fast is the top of the ladder sliding down the house? Well, the top of the ladder sliding down, is that represented by dx over dt, or is that represented by dy over dt? Well, of course it's dy over dt because the sliding down is the y. So how fast is y changing? Well, that's the derivative of y, right? Okay. So I've got this arrow here, dy over dt, right there. That describes how fast the top of the ladder slides down. So in the end, we're going to get a number for this. We're trying to figure out what number is this dy over dt. If we're trying to solve for that, it must be the case that we know the values of the other three unknowns, right? We're going to end up plugging in a value for x, plugging in a value for dx over dt. That whole thing is 1. And we're going to plug in a number for y. And when we plug those numbers in, we can then easily solve for what dy over dt equals. And we'll be done. Okay, so at this point, whatever you're looking for, it must be that you know the other parts to fill in. So you go back and read the question again carefully, and you decide what's what. So I won't scroll it back down. I'll just read it here. It says the 72-inch ladder is leaning against a house where the base of the ladder is 36 inches away. Okay, so we are looking at the instant when X is 36. Okay, so it's changing, it's sliding out, but at the instant X equals 36, that's when we want to know. That's the critical moment in question. So we're going to plug in now this is where we plug in the 36. We don't want to put that in our drawing because that would be misleading ourselves because it's changing, but now we will end up plugging it in because that's the snapshot at that very moment. How about dx over dt? Do they tell us dx over dt? Well, actually, it's right here in our drawing. It's the base of the ladder slides away at 5 inches per second. So we know that x is changing at 5 inches per second. So dx over dt, that whole thing just going to become a 5. Okay, finally, we need to know the value of y to plug in. Now, this is interesting. They don't tell us anymore. They told us x, they told us dx over dt, but they never told us what y equals at the moment in question. Well, that just means we're able to figure it out on our own. They didn't need to tell us what it was. So let me scroll up to about here. Okay, so y equals what? I don't know, but we can get it. We're going to use the original equation. By the original, I mean the one before we took derivatives. X squared plus y squared equals 72 squared. We're going to use that original equation with x equals 36. So it's at this moment. So hey, if I put that in, I can get y at the same moment on my own. I don't need them to tell me what it was. So it's kind of what we got here. We'll put that in. 36 squared plus y squared equals 72 squared. And I just did this in one step in my calculator. 72 squared minus 36 squared gave me 3,888. And then I took the square root like so. So y will equal the square root of 3,888. Now, I could simplify this. No problem. Some calculators will simplify that for you on their own. Or I could leave it like that. I know I'm going to round the answer to 2 decimal places when it's all said and done, and that's very common in this section when you get to applications. Usually you round your answer. You don't want to leave it in a square root form. Typically, fractions are often, fine, but usually we want to round our answers so we get a good idea of what these values are. Okay, so I'm just going to leave it like this. And now what we're going to do, we're going to plug these in. 36 for x, 5 for dx over dt, square root 3,888 for y, all into that equation. And I've got that on the next page. Oh, I actually copied my related rates equation, and then now I'm plugging those numbers in. X, dx over dt, y. And all I got to do is subtract that, divide by that. And let's see, this works out to be 360. So subtracting and then dividing here. And now finally, I'm going to round my answer to 2 decimal places. And I get dy over dt equals negative 2.89 inches per second is the units. Let's come back to that. We'll discuss how we knew that this was the units. But we got the negative 2.89. A couple of interesting things here. I'm actually going to go back to the drawing. For one, our answer makes sense, right? I mean, that seems like a realistic value, so that's a good thing. If we got like negative 200 inches per second, whoa, that might be too much, but negative 2.89, that's pretty close to 5, right? So the top is sliding down a little bit slower than how the base slides away. Okay, it makes sense because the way it's leaning. Also, just the fact that it's negative. Let's really make sense of that. We got a negative answer here. What's up with that? So if I go back to the drawing, it makes all the sense in the world that it should be negative. Look at x. X slides away. So as the ladder slides away, the value of x gets bigger. X is increasing as the ladder slides away. But what about y? As the ladder slides, doesn't the y decrease? So if y is shrinking, then its instantaneous rate of change should be negative because it's getting smaller. Where x is getting bigger, its rate of change is positive. But as y gets smaller, its rate of change is negative. Ooh, okay. And it's just something good to notice here. We expect to get a negative answer, and we did. The math matched what we would know to be true. But the thing is, usually, when you're asking that sort of question, how fast is the top of the ladder sliding down? We really are not thinking in terms of positive and negative. We're just thinking of like speed versus velocity. Velocity, we give a positive or a negative because it could be getting bigger, smaller, that sort of thing. But speed, we don't. We just think of speed as being like kind of like distance, like it's always positive. So it's completely appropriate to answer in the positive and just say 2.89 inches per second. So either of those answers totally acceptable. Lastly, okay, what about the units? It said to include units. How do we know it's inches per second? Well, everything they talked about here was in inches, and then they described dx over dt, right, as being 5 inches per second. So obviously that's a giveaway. But let's look even deeper. Now this is pretty cool. The Leibniz notation reveals what the units are here. Okay, this is not a fraction, but it sure does behave like a fraction right now. What are the units on y? Inches. How many inches up the wall, right? It's a distance. What are the units of t? Why do we even use the variable t? We use the t because it's with respect to time. Time is passing. Well, what are the units of time? Seconds. So it's literally inches over seconds, inches per second. And that's how you can figure out your units of a derivative. Literally take those units over those units, and you got it. Okay, that was great. These examples take some time to work through. We're going to stop here. We got a couple more to come.